Hello there. This is my first lecture with you. Before starting, I would like to introduce myself. My name is Siddharth Mukhopadhyay. I am currently an 11th grader and studying at St. Patrick's Higher Secondary School. So, today we are going to study a very interesting topic of chemistry, which has troubled me for a very long time. It is one of those concepts which I did not understand in the first read. So, I will try my level best to make you understand what I couldn't. Okay, so let's put up the chapter name: Chemical Thermodynamics. Okay, I hope you can see it on the board clearly. Now, before starting, I would like to tell a story because you need to know why you are studying this chapter. The story goes like it's our own story, it's the story of humanity. 1 million years ago, Homo neanderthals discovered fire, and that's what changed the course of whole humanity. Before that, we used to eat raw food. It was our daily consumption and we needed a lot of energy to digest that raw food. It was not easy to digest complex molecules not broken down. We had to break them down and digest them. But with the discovery of fire, what happened is we could break down that food outside the body for the first time. And this helped us reduce the energy needed for digestion, which in turn gave us more energy for other tasks. Now, this energy was utilized by our body to build up our brains, our thinking boxes, which made us more intelligent and developed our brains to become bigger and wiser. So, that's what changed the course of humanity. Now, the discovery of fire, how it happened, is not very clear. Some theories say that it was the rubbing of a limestone against another stone, which provided a spark and lit up a stack of leaves, dry leaves, which were nearby, and that's how fire was discovered. But that's not the main topic. What we are going to study is what happened after that. Heat was generated. Chemical energy of the wood and leaves was converted into heat. Why I'm telling you this? Because thermodynamics literally translates to the study of the language of heat flow. So to understand heat flow, you need to understand how it's intertwined with our own history. After that, we had the tools revolution, the first of the revolutions, and then this was the tools revolution. Fire was one of the tools that were discovered in this age. Now after that, we had the agricultural revolution. Here also, energy played a vital role. The energy from the sun, the heat energy and the electromagnetic radiations from the sun were used by plants and converted into starch, an edible material which we can easily digest. So, in agricultural revolution, this was exploited and we made use of this property of plants to grow, which were more feasible towards providing us with starch at a localized level, so that we did not have to travel much to get food from different locations, which saved travel time and provided us with surplus food which we can use at different times of the year, and saved a lot of time for us to indulge in other activities. So here also, heat energy from the sun was converted into something we know as chemical energy in the form of starch by plants, and this was used by us to produce food. Then there was Industrial Revolution. What happened in Industrial Revolution? you must be knowing, is very recent. In the 1800s to 1900s, this industrial revolution took place. We had the invention of the steam engine. Hydro energy has been used for a long time, before the industrial revolution too, but what transformed or gave pace to this revolution is the use of steam in generation of energy. This was a major breakthrough which changed our lives and made the standards of living level up. So it's very important to know how this has helped us in the past so that we can make use of this to change our futures. That's what the art of gaining knowledge is all about. Now, getting back to the topic, this heat has helped us all these years throughout everything in our history. So first of all, in chemical thermodynamics, we need to get familiar with few terms. I told you, this is the language of heat flow. So to understand a language, you need to be familiar with what terms are used in it. So first term I will discuss system. System is anything that is under focus, under study. So if you are studying something or you are giving your attention on that, then it's called the system. So for example, if you have a tub of water and you devote your life to study of this tub of water which is in this tub kept in your basement somewhere, and you devote your whole life to the study of this water. So this is your system. Now, anything outside this is immaterial for you because you have devoted your whole life to the study of this water. So, whatever is outside this, whatever is not this bucket of water, is your surrounding. So, if I represent this through a Venn diagram, this is your system and this is your surrounding. System plus surrounding, that is system plus surrounding, give you universe. Okay, universe is what the entire system plus surrounding thing makes up. Anything which is not the system is the surrounding, and it is not under focus or under our attention. It does not require our attention because we are only interested in the system. Okay, so I told you I will discuss one term, but here we came across another term, surrounding, and the union of these two is the universe. A bit of maths also. So this system plus surrounding gives us universe, and what separates this system from the surrounding, this wall, okay, and we call this wall the boundary. So another term which we came across for this, boundary. So we are going to discuss each of these terms in more detail now. Today is the introductory video, so it will not be much long. We'll just discuss the terms and have the next video talk about some internal energy, work done, and all these things. The main chapter. This is just the introductory video, but you need to understand these. System. Talking about the system. System can be mainly of three types. So we have open system, closed system, and isolated system. What happens in open system is, open system allows the exchange of both matter and energy. Let me explain with an example first. Let's take a tub of water which is being heated, okay, under a Bunsen burner. So you can see it is open, okay. So water is getting evaporated. Now this water evaporating is loss of matter to the surrounding, and this heat is getting into the vessel, and also heat is leaving this vessel. So there is energy exchange with the surrounding too. When there is both matter and energy exchange with the surrounding, both matter and energy exchanges are happening with the surrounding. This is our system which is under consideration. And if we are losing both matter and energy, or getting both matter and energy from the surrounding, that is transfer of matter and energy between the system and surrounding, then it's called an open system. That means it is susceptible to the changes in surrounding. Now, what is a closed system? Let me explain here. Now, we take the same vessel, and now what we do is we close it with a lid. We are heating it, but now what happens? The water vapor is not able to leave the container. So, matter exchange is not possible. But energy can still be radiated out and be conducted through the walls of the container. So, energy is not being held back. So, energy exchanges are happening. Now, what are we talking about isolated systems? Let's take a thermos flask, okay? So some liquid is kept in this thermos flask. Now there is insulation, insulated walls. These walls are known as adiabatic walls. If heat exchange is allowed or energy exchange is allowed, it is known as diathermic walls. These are few terms which you need to keep in mind. Now, insulated walls are known as adiabatic walls, and they do not allow exchange of heat with the surrounding. So, first of all, it's a closed vessel, so matter exchange is also not possible. And second, energy exchange is also not possible because of insulation. Definitely some energy exchange will be there, because 100% insulated vessel is not able to be made with our current technology. But definitely it can be assumed to be that there is no energy exchanges taking place, and so there is this is called an isolated system. Now, let me talk about the second term which we discussed. I hope the system part is clear. If you face any doubts, you can reach to me with through the comments anytime. Now let's discuss about surrounding. Wall, boundary. Okay, boundary can be classified in two ways. First, it can be classified as rigid and flexible, and then it can be classified as real and imaginary. Okay, so if I take the same example of the water, this is a real boundary. It's a wall. And this is an imaginary boundary between the air and the water. This imaginary boundary is flexible, but this real boundary is rigid. You get the point, right? So this is talking about the boundaries involved. Now let me pose you some questions and you will have to answer those. First question. If I talk about the universe as my system, I'm taking the whole universe as my system. So, is it isolated? Is it open? Or is it closed? What type of system is it? Okay, that's spelling mistake. So, what type of system is it? Pause the video if you need to think. It's okay. Should I reveal the answer? Yes, okay. It's isolated. Why? Why do I say that? Because if I take the whole universe as my system, then there's definitely nothing outside the universe. If you don't take the multiverse into account, definitely it is not taken into account, but the whole universe is what the whole observable universe is what is perceived by us, and we know that there is nothing outside the universe because we can't see anything outside the universe. These are just theories, okay? These are just theories of the multiverse and parallel universes, but actually it is a null set. So if it is a null set, then surrounding is a null set. If surrounding is null, then universe, the matter and energy can't exchange with anything because there is nothing outside the universe. So this remains constant, matter and energy. Okay? Now, another question. Second question. Let me take a refrigerator. Okay? You have this refrigerator. The door is open. Please don't mind my drawing. Okay? So, you can take out anything from this refrigerator. You can take out this. Matter exchange possible. And energy, heat is getting into the refrigerator. You don't say cold is getting out of the refrigerator. Cold is nothing but the essence of heat entering. So, energy exchange is also possible. Right? So, this is an open system. Now, this was pretty easy. But my next question, you take the same refrigerator and now you close the door. What type of system is it? Think. You need to think yourself to develop your intelligence. What type of system is it? Is it open? Closed? Isolated? makes me also think. Well, some of you might guess matter exchange is also not happening. Energy exchange is also not happening because there is no exchange happening. I can say that this is an isolated system. Is it correct? Or if I say it's an open system because I can open the fridge and take out the things. Another thought might be that too. Some of you might think like that. When you don't open the fridge, I'm talking about. So that possibility is completely not right. We are talking about the closed fridge as our system, not the open fridge. This is our system. So, definitely matter exchange is not happening because it's closed. You cannot take out anything from the fridge. Matter exchange is null. But talking about energy exchange, is energy exchange happening? Think about it. Quickly pause the video and go to the nearest fridge, okay, and see, study it. Is energy exchange happening? Yes, it's happening. How? When you talk about the back side of the fridge, it's written hazard, don't touch, because heat is being ejected out from the back part. The heat from inside is going to outside. That is how they keep the fridge cool, because they are constantly giving out heat from the inside to the outside. Heat is being taken out from the system and left into the surroundings. So energy exchange is happening. Therefore, we can say this is a closed system. Okay, I hope you were able to understand. Think about it intuitively. Explore other examples around you. A cup of tea maybe. Matter exchange? Yes, possible. Energy exchange also possible. So yes, it's an open system. A cup of tea is an open system. Now, after system, surrounding, universe, boundary, all these terms, we are talking about state. Okay. What is a state? Now there are some parameters. Pressure, volume, temperature, then mass. All these parameters define the state of any system. So, if I take some gas with a piston above it, piston is nothing but a lid above it, which you can push or pull out. So, it's kind of used to change the pressure. So if you don't apply any force, then external pressure is equal to the internal pressure, which is equal to 1 atm. So let's suppose this system is in state A. And how do you define state A? P1, V1, T1. P1, V1, T1. Pressure is P1, volume is V1, temperature is T1. If I change even one of these parameters, just one, not needed to change all, if I just change one of them, then this system shifts into a different state, state B say, where T1, V1, let's say change the temperature to T2. So this is a different state. Okay, I hope you understand the concept of state. Now these states are only possible when the system is in thermodynamic equilibrium. What is this thermodynamic equilibrium? Now let's understand thermodynamic equilibrium, a very lengthy word but very easy to understand. Don't get stressed out. Now, thermodynamic equilibrium. Before understanding thermodynamic equilibrium, let's understand three other equilibriums. First, mechanical. Second, chemical. And third, thermal. These three equilibriums we need to understand. What is mechanical equilibrium? When the force, the net external force and the net external torque on a system equal to 0. Okay? That's when it is in mechanical equilibrium. It can be said to be in mechanical equilibrium. What is chemical equilibrium? When the the system is in chemical equilibrium with the surrounding. That is, no chemical reaction is taking place which is changing the chemical composition of the system. The chemical composition of the system has become constant. Then it is called, it is said to be in chemical equilibrium. Now, what is thermal equilibrium? When it is having the same temperature, that is, no heat exchange with the surrounding. Temperature difference is 0 with surrounding. So no heat exchange with the surrounding. Now, some people are confused in the very basic definition of heat and temperature. How they influence each other. Right? I was too. So, I will discuss this. But before that, you need to understand that what is mechanical equilibrium? Summation of force is 0 and summation of net external torque is 0. Constant chemical composition, no change in its chemical composition of the system, and no heat exchange with the surrounding. These three. Why I discuss these? Because all of these three taking place together is what is thermodynamic equilibrium. Nothing else. Just three different equilibria taking place simultaneously is thermodynamic equilibrium. If a system has mechanical equilibrium, chemical equilibrium and also thermal equilibrium, then it is said to be in thermodynamic equilibrium. So a state, and you need to understand this, a state of a system is defined only when it is in thermodynamic equilibrium with surrounding. If it's not in thermodynamic equilibrium, then you cannot define its state. Okay? There should be no heat exchange with the surrounding, no net external force on the system, and no change in its chemical composition. If these three hold true, then it is said to be in a particular state. If at that point pressure is P1, temperature is T1, and volume is V1, then that's a particular state of that system. Okay? This is about thermodynamic equilibrium and state. Excuse me. Now, let's talk about processes. What are processes? I hope you understood this. Okay? Processes. So you have these many terms floating around in here. Okay? I think 4 of them. Isothermal, isochoric, isobaric, adiabatic. Okay, some foreign language seems like. Okay, so let's understand each of these terms one by one. Let me give a brief overview of all these and then we will study them in detail. Isothermal. In isothermal process, the temperature of the system remains constant throughout the process. Let me first define a process. What is a process? Process is transition of a system from one state to another. When a system is transitioning from state A, suppose, to state B, then it's called a process. If during the process temperature is constant, then it's called an isothermal process. Other parameters like pressure, volume may change. It's not compulsory that pressure, volume might be constant. Temperature constant, then it's isothermal. Similarly, if volume is constant, then del V. Del V is constant, del T is 0. T is constant, then it's isothermal. Del V equals 0, that is V is constant, then it's isochoric. It should be throughout the process. It's not like you decrease the volume and then again bring it back to the same volume at the final stage, then it can be called isochoric. Not that. Throughout the process, if volume is constant, it doesn't change a bit, then it's isochoric. If del P equals 0, that is pressure, there is no change in pressure of the system, then it's isobaric. And then if del Q is 0, that is there is no heat exchange with the surrounding, then it's adiabatic. If you recall, I had told you that whereas there is this thermos flask with insulated walls, these insulated walls are called adiabatic walls, and if it's not insulated, if it allows exchange of heat and energy, then it's called diathermic walls, if you recall. Now these adiabatic walls, adiabatic means no heat exchange. And what is this iso? Actually, whenever a parameter is kept constant, you add iso to it. Iso translates to same in English language. Isothermal, thermal means temperature. When temperature remains same, then it's isothermal process. When volume remains same, then it's isochoric process. When pressure remains same throughout the process, then it's isobaric process. And these are parameters that define the state of an object. Temperature, volume, pressure, these define the state of an object. Heat doesn't define the state of an object. So this is not a state variable or what we say a parameter defining the state of a system. So we call this adiabatic process, where no heat exchange is taking place with the surrounding. Now let me make the concept of processes much more clearer with the help of a graph. Graphs always make the concept much more crystal clear. So processes, we define them as transition of a system from one state to another state. Okay, understand this? After this, let me draw this graph. Y-axis, x-axis. Along y-axis, let me take pressure. Y-axis, volume. Add another axis, z-axis. Let me add temperature to it. Okay? Pressure, volume, temperature. Suppose there is this point in this space which has pressure P1, temperature T1, and volume V1. And there is another point in the space where it's pressure P2, temperature T2, and volume V2. None of the parameters are constant here. But this is also a transition from one state to another. And there can be, these curves represent various paths taken to reach from this state to this state. So there can be infinite number of processes to reach from one state to another. I can draw infinite curves to reach from this state, let's call it state A, to state B of the system. I hope you understand what's happening here. Now, just expand your imagination and think, what if the temperature was constant? Just think. Yes, isothermal process, right? This is the general definition of a process. Transition from one state to another. Here all the parameters are changing. Pressure along the y-axis is changing. Volume across the x-axis is changing. Temperature along the z-axis is changing. But if you fix the temperature, and if you fix the temperature, then it turns into from a 3D problem to a 2D problem. Just turn this. If I take the temperature as just T, you just turn these axes and you see that it's just a line, nothing more than that. Okay, let's suppose this is temperature T on the z-axis. This point is also at temperature T. This point is also at temperature T. So they lie in the same plane of the temperature. Okay, in the same plane. I hope you can see this plane. It's lying in the same plane. This temperature plane is becoming a side of the PV cube. Okay, it's like lying on the XY plane. No difference. Just the temperature becomes constant. It's parallel to this plane, this XY plane. That is the PV axis plane. It becomes parallel to that. So if I just turn these axes and get the temperature axis to point right into the screen, just into the screen, then what happens is it's pointing into the screen. So you get something like this. This is an isothermal curve, or you call it an isotherm. Okay? From P1 V1T to P2 V2T. I hope you understand. Now let's understand isothermal processes first in much more detail with a few examples. I hope you are not getting tired. I will really advise you that you, after each topic covered, you just pause the video and try to recall each and everything I said, so that it's a quick revision of the topic you just learned. This recall method works wonders. Just try it once. It will help you to remember the concepts you learned in a much better way. Now, that's what we are talking about, isothermal process. Isothermal means the temperature remains constant. Okay? We are going to just cover the processes part and talk a bit about heat and temperature. Very basic definition of what heat and temperature it is, and a few questions, very few intuitive questions to help you understand them on a deeper level. Okay, we are going to finish off with that. So let's just sum up the isothermal process. So if we take the PV curve, according to Boyle's law, when temperature is constant for a gas, PV is constant. That is P directly proportional to 1 by V. Just Boyle's law, nothing new. Excuse me. So, if I take this example with a piston and I place a brick over this, so external pressure increases, this is P external. This pressure is pushing it down and it will continue down. These gas molecules are inside here. Taking an ideal gas. These gas molecules, this possess some kinetic energy. When you decrease the volume, the collisions between these molecules increase. Okay? When you are decreasing the volume, the collisions, that is the space for these, are decreasing. If you push some people into a already filled up train, then it will create a lot of collisions, right? So pressure is increasing. Pressure inside the container is increasing, and it will keep on increasing till it becomes equal to the external pressure. And then when internal pressure becomes equal to external pressure which is being applied, the piston will stop. Suppose it stops at some place like this. Okay, it comes down. So the volume has decreased. When volume has decreased, the collisions have increased. Okay, so the kinetic energy is increased. When the kinetic energy increases, the temperature increases. But the temperature doesn't increase here. The reason is these are diathermic walls. So when kinetic energy increases, heat is lost by these walls. Because these walls are diathermic walls, what happens is it doesn't let the temperature increase. Instead, it lets out heat into the surrounding, which makes the temperature remain same, that is constant. So we are decreasing the volume, increasing the pressure, but what is remaining constant? Temperature. As temperature remains constant throughout the process, this as a whole is an isothermal process. Let's understand again why the temperature is not increasing. When you are pushing down, there is this break here also. But now the internal pressure has become equal to the external pressure. Okay? P external has become equal to the P internal. So this piston has stopped. Now, as on both sides pressure is equal, so pressure difference is now 0. But while the pressure was increasing, volume was decreasing. When volume was decreasing, the collisions between these molecules, in these gaseous molecules inside of the container, they were increasing continuously. And when collisions increase, the kinetic energy of the molecules increase. When kinetic energy increases, heat is generated, which raises the temperature. But in this case, temperature doesn't increase. Why? Because these are diathermic walls which let out the heat into the surrounding. The heat which got accumulated due to increasing kinetic energy of the molecules inside the container, this heat was given out into the surroundings, which made the overall temperature remain constant. So there was no increase or decrease in temperature, and so we call it isothermal. So you see this graph? This is the graph for Boyle's law, and this is also the graph for isothermal. I gave you the three-dimensional representation. If I draw the temperature axis here, so in both the cases they lie in the same plane. So temperature is same for both these states. Now let's talk about another one, which is isochoric. Let's understand this also with an example. Let's take two examples and understand them together. Isochoric and isobaric. pressure and volume. Isoporic, isobaric. So I take some water. Okay, not some water. This time, let's do something. Let's make it interesting. Every time water is not fun. Okay? Let's take some chicken soup, okay? Looks more like fish. Sorry. Okay, chicken soup. And we are heating this. Okay? There's open lid. So this is an open system. Clearly identifiable. And afterwards. So, and another place, we take a pressure cooker with its lid on and also heat this starting at the same time. So these were in the same states. They had the same pressure and volume and temperature at the starting, and we started heating them. This pressure cooker contains some rice. In the case of this one, it's in contact with atmosphere and it's 1 atm pressure. P external 1 atm will be equal to P internal, which is 1 atm. So throughout this heating process, pressure will not change. The volume may increase due to heating. Let's suppose this was initial volume and this increased to this point. So volume increased but pressure remained constant. So this is isobaric. What about isoporic? Here in the pressure cooker, the volume remained constant, but the pressure kept on increasing inside. So the volume of this rice water remained constant, but the pressure inside the cooker was increasing and increasing. So we call it isoporic because the volume remained constant. So that were the two processes, isoporic and isobaric. Let's understand them, the graphs. Excuse me. In isobaric, let's take P here, let's take V here. Let's suppose it goes from this volume to this volume. Temperature is also continuously changing, but I will show you with two axes only. Let's not make it more complicated. Here is the temperature axis. But okay, let's suppose this was first at this temperature and then later it went to this temperature. So the plane is a bit like rotated towards this side. Okay. So volume change from V1 to V2 it increased, but throughout the process the pressure was same. Okay. The pressure remained same. Now let's talk about this one. In isoporic process, volume remains constant. an obvious question when I studied this is why you are taking pressure and volume on this side and pressure and temperature on that side. Why you are not taking pressure and volume? Why? You should take pressure and volume only. But when you take pressure and volume, like you have been doing till now, the curve comes like this. Now, if you take out the slope of this, the slope is undefined. So we want a curve which has a defined slope, not an undefined slope. That is why we don't tend to take this PV curve for this one. Okay? We are always trying to get to defined values. So in this case, the temperature is 0. In the PT curve, the pressure volume, it goes from P1 V1, let's say, to P2 V1. The volume remains constant. If I take the volume axis on this side, both of them lie in this plane. Okay, you understand? So they are in the same plane of the volume axis, parallel to the PT plane. I hope you understand these two graphs. Now, let me get to the last process, that is adiabatic. If I ask you, in a thermos flask, what is the process taking place? Is it adiabatic or isothermal? I believe many of you will be tempted to answer isothermal, but the answer is not actually isothermal. Actually, it's adiabatic. In isothermal process, recall what I said, they have diathermic walls, so that heat generated can be lost, so that temperature doesn't increase. But in this case, I have adiabatic walls in a thermos flask. Okay, so don't allow heat to be lost into the surrounding. So if I compress this also with a brick placed on it, the kinetic energy increases, but there is no loss of heat to the surroundings. So if no heat is lost to the surroundings, it will definitely raise the temperature. Okay, so this is an example of adiabatic. Now, I will ask you a few questions and you have to answer them. First question. Define heat and temperature. Elementary school question, right? No problem. Define. Okay, I can't hear, but I believe you are telling the right answer. Heat, mode of energy transfer when there is temperature difference between system and surrounding. Okay, what is temperature? Degree of hotness or coldness of a body. as the most elementary definition of temperature, but is actually, you can define it much more aptly by saying that measure of average kinetic energy of the system. Okay, so now I will do a verbal what do I say, one-sided talk, which I believe you will answer back, and I will request you, after every question, just pause the video for 2 to 3 minutes and just think on the possible answer of the question. This will help you only to develop your thought process and your thinking. I ask these questions, that is why today I can also ask you these questions. So always try to ask questions which will help you to gain more insights into the topic you are learning. Asking questions always helps in better understanding of the topic. So, if I ask you, suppose there are two bodies, A and B. They are at the same temperature. That is, they are in thermal equilibrium with each other. Okay? Excuse me. They are in thermal equilibrium with each other. So, if I ask you, is their heat content the same? Do they contain the same amount of heat energy? If their temperature is same, is the heat energy contained by the two bodies same? Think. They are at the same temperature, but is their heat content same? Maybe yes, maybe no. What do you think? Think. Pause the video. Hope you thought. Now, let me reveal the answer. Well, heat content depends on various factors. One of them is definitely temperature. Now, heat flow, you have to understand this. Heat flow takes place when there is a temperature difference between the two bodies. But heat content depends on definitely temperature, but it also depends on the mass of the body, the specific heat capacity of the body, the nature, material of the body, and all these factors. So, let me explain this with an example. Suppose I take a cup of tea. Excuse my drawing. This is a cup of tea, and I take a 30-liter bucket of tea. They both are at the same temperature, but do they have the same heat content? Definitely the teapot will have lesser heat content than the bucket of tea. They are in thermal equilibrium with each other. No heat will flow when they are kept close to each other. But this has more heat content than this. And this brings me to my second question, which I immediately asked when I studied this. My second question: if these two are at different heat content, why is not heat flowing from the higher heat content body to the lower heat content body? Why is not this happening? Pretty logical question to ask. Why is heat not flowing from this body to this body? If this has a higher heat content. Why is only temperature playing a role? So actually, only temperature plays a role. The answer is actually that only temperature plays a role. And let's understand this through an analogy or a metaphor. Okay. So, I have this tower, and on the top of this long turret, there is a water tank with 10-liter water. And there is another turret of the same height, and it has 5-liter water. Now I connect these two with a pipe. Okay. To understand this, that there will be no water flow between these two, net water flow, because they are on the same height. They have no pressure difference. So if there is no pressure difference is what is required for water flow. It is essential for flow of water. If there is no difference in the pressure, then why will water flow from this side to this side or that side to this side? So, if imagine the mass of this or the volume of this water is comparable to the heat content. The heat content is same. The heat content is different. The volumes of these two are different. But now you consider the height. The height is same, and that is the temperature. The pressure on both these is same, so there is no height difference, and therefore the temperature is comparable to the height, which makes the water not flow from this side to this side, or vice versa. It definitely has greater volume than this one, but greater volume doesn't mean water has to flow. Same way, greater heat content doesn't mean temperature has to, means heat has to flow. Temperature is what decides. The height of the turrets is what decides whether heat will flow or not. Let me explain with another metaphor. Suppose, excuse me, there are two people, person A and person B. Person A also has rupees 10,000 rupees. Person B also has rupees 10,000 rupees. I said rupees 2,000. Sorry. Rupees 2,000, and person B also has rupees 2,000. 10,000. Both of them have 10,000 rupees. Now this person has them in form of 100 coins, and this person has them in the form of 5 notes. Now both have 10,000 rupees. The heat content is same. It is comparable to heat content. The wealth of both of them is same. But one has them contained in 100 coins. So each coin is worth 100 rupees, and each note of person B is worth 2,000 rupees. Okay? 100 rupees and 2,000 rupees. So heat content is different, but the worth per coin or per note is different for both of them. Now this is comparable to temperature. Okay, temperature will the heat exchange will only take place, that is, they will exchange if they both had 100 coins, if they exchange one coin with one another, then what is the net exchange? It's zero. Each coin of this person also is worth rupees 100 and this person is also worth rupees 100. So if he gives one coin to that person and takes one coin from that person, then the net exchange is definitely zero. So if the worth per coin or per note is the same, then temperature difference is zero. But here is not that case. Here they are different. So temperature is different. If this person gives him one coin and takes one note, then there is a net increase or decrease in the wealth of these two people. So their heat content is changing. It is only possible when their temperatures are different, when heat will flow from one body to another. Okay? So temperature can be understood as the energy per particle. Like it is the worth per coin. You can understand this as energy per particle. This is one way to understand what it's all about. This is the total energy. Heat content is the total energy of the system, and temperature is like the average, the energy per particle of the system. Right? Now, let me ask one last question. In winters, suppose it's a long night and the temperature during the night, you have seen on the weather app, it's 5 degrees Celsius outside. So you go and you know that steel and wood, two things are kept outside, and both of them have been kept outside for a considerable amount of time, so that they are in thermal equilibrium with the environment, which means both have a 5 degree temperature. Now, you take this steel and you take this wood. First, you take your hand and touch this one, and then you touch this one. Okay? Which one will feel colder? You get it right, the question? Which one will feel colder? Steel. That's not the question. Why will it feel? That's the question. Why will steel feel colder? Think. Again, you are thinking about it. Because. What's the reason? Think. Then see the answer. Because steel has thermal conductivity, which is higher than that of wood. Steel has more thermal conductivity than wood. So when you touch steel, heat flows, the rate of heat flow from your hand into steel is faster. As because it is faster, for the same amount of time, more heat is lost from your hand when you touch steel than when you touch wood, because wood is insulating, right? So that's why when more heat is lost from your hand, the skin feels much colder. That's the answer to this last question which I asked. Now, I would like to end this session. So before ending, I would like to say that thanks for seeing till the end. And next class, we will be studying about internal energy, work done, different types of work done, and ZLOT, zeroth law of thermodynamics. Okay, thank you. Bye.